Who has a question? Yes.
So we have introduced the longitudinal proper time, right?
Yes.
And if you calculate the gamma factor out of this proper time, it would be only the gamma factor in longitudinal direction, right?
The gamma factor has to do with velocities, not with time. So I'm not sure what. Oh, you mean the ratio of the tau? Yes, that ratio would evolve only. Yes. It's the gamma factor. Well, in a sense, it's the gamma factor associated with the pure Kane scaling profile. So if you take into account the longitudinal expansion according to this scaling ansatz, where the rapidity of the flow is equal to the space-time rapidity, it would be the gamma factor associated with that part of the flow, not in taking into account transverse flow. Well, the longitudinal proper time is still a useful variable to separate off the dominant longitudinal flow, but then you have to take into account, so the gamma factor will be actually a product of two gamma factors, one associated with the longitudinal expansion and one associated with the transverse expansion. Good question. Yeah. That was one, okay, good. I said I need three to proceed. Yes? Yes, that would come towards the end of the course, but I may never get there, so let me answer it right away. So thermalization leads to a buildup of a thermodynamic pressure, and then because the pressure exists only where the medium is dense and hot and not outside, there is a pressure gradient, and that pressure gradient leads to collective flow, and you can measure that because the collective flow gives, if you think about it non-relativistically, it gives every particle an extra boost m times the flow velocity, and so different particles with different masses get a different boost from that flow velocity, and you can check that. You can check in the particle momentum spectra that they don't have the same shape for different particles, but that there is a hierarchy of slopes that tell you that the heavy particles are moved to higher PT than the lighter particles. So you see evidence, what we call for radial flow. Radial means transverse to the beam direction, but azimuthally symmetric in the transverse plane. Then there are anisotropies in that pressure because the nuclear overlap is usually not complete. For that you would have to have a central collision, and these are extremely rare. All generic collisions have some finite impact parameter. Then the region in which you overlap looks somewhat like an almond shape, and so the pressure falls off from the peak in the middle to zero on a shorter length in the short side of the almond, and on a longer length scale on the long side of the almond. So if this is the overlap region, you have very high pressure here, P max, and you have P equals 0 here, then the pressure gradient is steeper along this direction than in that direction because it falls off to 0 faster, and that means you get more flow in this direction and in that direction. And so you see that flow effect that I just told you about more strongly in one direction than in the other direction, and that is also seen in the experiment. Now, you can make a theoretical argument, and that's something that will come out from what we do today, that the efficiency of translating these pressure gradients into anisotropic flow depends on how strongly the medium is interacting. And the stronger it interacts, the smaller is its viscosity, the closer it gets to local equilibrium. And the stronger the conversion efficiency is. So you get the largest flow anisotropy for the most ideal fluid. and you get less of a flow anisotropy if the fluid is less ideal and there is larger mean free path in the system. And so you measure the magnitude of that anisotropic flow, and you compare it with what you would expect from ideal fluid dynamics, and how close you are to that limit tells you how close the fluid is to being ideal and locally thermalized. And that's how we know that the system is very closely thermalized. We know that the viscosity, which describes the deviation from local equilibrium, is almost as small as it could possibly be, and also that's something that I discussed. So that's the short answer to the long story. Third question. Well, 2 out of 3 is not bad, so let's go on. All right, so here, this was still left here, which surprised me because I thought there was a seminar in the afternoon. Light. Okay, thank you. So we said that we divide the heavy ion collision evolution into 3 stages: a pre-equilibrium stage, a quark-gluon plasma stage, which is in approximate thermodynamic equilibrium, and as a consequence of that, we can actually describe it macroscopically by hydrodynamics. And then once the energy density drops below about half a GeV per cubic Fermi, the quarks and gluons combine into hadrons, and those hadrons interact with each other by scattering. This interaction is much less strong than the interaction between the open color charges of the quarks and gluons in the quark-gluon plasma. So the system is not as well described by hydrodynamics over there in the late stage. You better switch to a description, microscopic description of bouncing hadrons, and eventually the system becomes so dilute that the bouncing stops and the hadrons escape as the particles that you see in the detector. So most of my lectures will be associated with describing with a hydrodynamic description. It also takes the largest time in the evolution. This here is, I said, restricted to something like 1 Fermi over C. This time scale is of the order of 10 Fermi over C. That's how long it takes when you start with the initial temperatures that you can reach at RIC or the LHC. At RIC you reach about twice the critical temperature for deconfinement. At the LHC you reach maybe about 3 times the critical temperature. So it takes about 10 Fermi over C in a central collision until you get down back to the hadronization point. Then there is another 5 or 8 Fermi over C of hadronic rescattering, which doesn't do as much to the momentum distribution as the earlier stages. So the bulk of what happens in the collision is controlled by this quark-gluon plasma stage once you get to top RIC and LHC energies. When you're at lower energies, then the lifetime of the quark-gluon plasma shrinks because you don't start at quite as high energy density, so it doesn't take as long to get you down to hadronization. And that means all of this moves down, and a larger fraction of the dynamics is controlled by hadronic dynamics and a smaller fraction by quark-gluon plasma. And eventually, when you go to the lowest end of the RIC energy regime, or back to the energies that were covered at the superproton synchrotron at CERN 15 years ago, then you end up in a domain where the quark-gluon plasma signatures get buried under stuff that is generated in the hadronic phase, and it becomes very hard to recognize them, even though we now believe that quark-gluon plasma is probably made all the way down to SPS energies. It just lives only for a very short time at that lower energies, and therefore it's hard to prove its existence in an unambiguous fashion. Let me start saying a few words about the pre-equilibrium stage. So the pre-equilibrium stage, as I said yesterday, we don't have a complete understanding of how it evolves, but we know that its energy densities initially are very large, so they are much larger than 1 GeV per cubic Fermi, so maybe 30 to 300 GeV per cubic Fermi. And if you want to describe that in terms of quark and gluon degrees of freedom, then you find that you have very high occupation numbers. That means every momentum mode is very highly occupied, and in that case, a description in terms of particles, especially since these degrees of freedom interact strongly with each other because of the high density, a description in terms of particles is not very adequate, and it's more convenient and more reliable to describe this as a field theory, as a bunch of quark and gluon fields, and especially gluons are very, very dominant in this early stage. And in the limit of macroscopic application numbers, this field theory becomes a classical field theory. So you would have classical SU3 Young-Mills equations. And this is called, this type of approach is called the plasma approach, because it starts from something that has been labeled a color condensate, a class, color class condensate, a classy state of quarks and gluons, which very high occupation numbers, slow collective dynamics compared to the microscopic dynamics there. That's the classy state, and color, of course, because it's made out of color degrees of freedom. And the transition of this initial color class condensate state, which one thinks is preformed in the existing nuclei, in the colliding nuclei, the transition from that color glass condensate state to the plasma state has been labeled plasma by McLaren and Lappy. And its evolution is basically controlled by solving the classical Young-Mills equations with quantum fluctuating corrections to that. And what we know about the classical Young-Mills equations is that they, because of their non-abelian nature, they are chaotic. Their solutions are chaotic. And in particular, if you have a system that has any kind of anisotropy in momentum space locally, then this anisotropy in momentum space gives rise to unstable, to exponential growth of unstable modes. And this growth is only stopped once the system has gone back to local momentum anisotropy. So any kind of momentum anisotropy gives rise to the growth of these unstable modes, and the result of these growing unstable modes is to drive the system back into local isotropy. And so we have plasma instabilities, which lead to local momentum isotropization. And then once the system is locally momentum isotropic on a somewhat longer length scale, you get thermalization, which means that the momenta are not only isotropic, but you get an exponential distribution in energy. You get energy equipartition. But the sequence of processes is first you get isotropization, then you get thermalization. And there is a hierarchy of timescales between that. And this timescale for isotropization, we believe, is faster than the timescale for thermalization. In particular, if in the asymptotic freedom regime, where the coupling constant of QCD can be assumed to be small, then you have a clear length scale separation where this goes a lot faster than this. In our quark-gluon plasma that we make at RIC, where the coupling constant is not that small, it's not clear how it's not known at this point how strongly these two timescales are separated from each other, but generically you expect the isotropization to happen before thermalization. It turns out that for the applicability of hydrodynamics, you only need isotropization. You don't need thermalization. It's something that I myself didn't understand for a long time, but I will show you today how this comes out from the microscopic understanding of what's going on. So, yes.
Which is the time scale in Fermi for isotropization?
We don't know.
Because one very often finds parametric estimates, but not the...
Yeah, we don't know. So the numerical simulations exist of these instabilities, and if you do it in a weakly coupled system where you have control over what you're doing, then isotropization takes too long. It takes about 5 to 10 Fermi over C, which is not enough to reach the degree of hydrodynamic behavior that we see phenomenologically. If you try to drive this to larger coupling, this is something that has been recently tried by François Gély and his student Thomas Eppelbaum. Then you find isotropization time scales on the scale of 1 over the saturation momentum, which is about 0.2 Fermi over C, so very much faster time scale. But that approach has been criticized because it makes some approximations that are out of control when you go to that kind of large coupling. So we have to continue working on that and see what the time scales really are. We don't really know at the moment, but the expectation is that actually when you do it right, the time scale will be pretty short. We'll see. Lots of room for PhD theses here. Okay, so I will now, this is actually almost everything that is known with some kind of rigor about the pre-equilibrium stage. And so we know it's somewhere between weak coupling and strong coupling, but we don't know exactly where. And the end result must be something like pretty well locally isotropized state, where pretty well actually is not such a big criterion. We can see that hydrodynamics, as long as you allow for viscous corrections, can start to work when you have almost 50% differences between longitudinal and transverse pressure, for example. So relatively strong anisotropies are still allowed, and you can already start describing things hydrodynamically. So as long as this isotropization time scale is of the order of 1 Fermi over C, maybe even 2 Fermi over C, it might still mean that what we have been doing so far with using hydrodynamics starting from somewhere around 1 Fermi over C may survive all of this. In any case, it has worked very, very well as far as the description of experimental data goes, and so we have a high degree of trust that eventually that's where the theory will converge to. Now, the quark-gluon plasma stage and the description of the quark-gluon plasma stage in hydrodynamics is something that I really would like to tell you a lot about in great detail, because that is something that is now being done in many, many different groups. So it's an approach that is being used in many different variations, and when you start reading the literature, not everybody does things the same way, and I will explain why not. And it's and you have to understand where the differences come from so that you can correct for them in your mind when you start making comparisons between different groups. Now, hydrodynamics is a macroscopic description. It propagates macroscopic thermodynamic fields such as the energy density or the temperature or the chemical potential or the baryon density, and it has a flow velocity associated with every point. This is possible when the microscopic momentum distribution is approximately thermal. So when it's approximately an exponential function of the energy, e to the minus energy over temperature. That's the Boltzmann distribution. And if that's the case, then there's only one number that you need to characterize that distribution. That's the slope, and that's the temperature. And that's the quantity that is then macroscopically evolved as a function of time. If the system is not in local thermal equilibrium, then this distribution function, f of x and p as a function of energy, say, is, so if you plot that on a logarithmic scale, in thermal equilibrium, this is proportional to e to the minus energy over the temperature, and so it's a straight line in this log plot, and the inverse of the slope is that temperature that you want to know. If the system is not in equilibrium, then maybe the distribution looks somewhat like that. And then it's clear that you cannot just describe it by one parameter. So you need additional parameters. And the more the system goes out of equilibrium, the more microscopic parameters you need to characterize this distribution function. And at some point, a macroscopic description becomes completely impossible. In that case, then you have to look at the evolution of that distribution function directly. And this is controlled by the Boltzmann equation. The Boltzmann equation says that p mu d mu f of x and p is given by some collision term f of x and p. So d mu is d by dx mu. If you write this out, p mu d mu, then this is e times d by dt plus p vector over e times the gradient. And so it's d by dt plus v dot gradient, and that's how you probably have seen the Boltzmann equation in non-relativistic context. The right-hand side is the collision term. If the collision term is 0, if there are no collisions, then the particles are just freely streaming. So the collision term describes the interactions among the particles. This assumes that you don't have any long-range forces. If you have an electron-ion plasma, for example, you can have long-range magnetic fields or long-range electric fields. Then you have, and these long-range electric fields will accelerate the particles, so they will change their momenta. So you will have to add another term that changes the momenta in there. In the quark-gluon plasma, we don't believe that we have long-range fields, because any kind of long-range field gets very, very quickly destroyed by color rotation processes, which happen very fast and make the system locally color neutral. And so we believe that we don't have to take these into account. These long-range fields are important once you go very anisotropic. Then these instabilities are a response to these long-range fields. But once you have reached a degree of isotropization, they are gone. So I'm staying with that stage of the collision where they are gone. Now, in the relaxation time approximation, RTA, you simplify that collision term as p dot u of x over some relaxation time, which can depend on x and p, with a minus sign times the deviation of the distribution function from an equilibrium distribution function, u. Yeah, let me just write it like this. So you linearize the collision term in its deviation from local equilibrium and parameterize the effect of the collisions by a relaxation time, which is the time scale on which the collisions lead the system back to equilibrium. And that flow velocity u mu of x is something that characterizes the equilibrium distribution function in the way that I will show you in a couple of minutes. So that's basically the flow velocity of the system in its equilibrium stage. So that is a very simple approximation to the collision term, which makes the calculations a lot easier. You cannot always use it, but you can basically get the correct structure of the hydrodynamic equations by making this simplification here. There is 3 important time scales that we have to watch and that we should discuss in order to understand the different dynamical limits that we can encounter. So we have 3 length scales in the system. The first one is the thermal wavelength, lambda thermal, for a system that is basically consists of massless degrees of freedom, like quarks and gluons. There is only one scale in the system, which is the temperature. All the masses are negligible relative to the temperature. And so just by dimensional analysis, you can see that a length, if you want to describe it in terms of a parameter that, like the temperature, it has to be proportional to 1 over the temperature. So for hotter systems, the thermal wavelength shrinks, and that's the first fundamental length scale The second fundamental length scale is the mean free path, lambda MFP. So that tells you how far particles can travel before they collide. And this is given by 1 over the average over the velocity distribution or momentum distribution of the particles of sigma times v times the density. So the higher the density, the shorter the mean free path. The higher the collision cross-section, the shorter the mean free path. And what is actually mattering is the so-called transport cross-section, which is the product of the cross-section times the relative velocity of the two particles when they collide. And so this is the mean free path. Question? Yes, okay, so this is, not lambda mean free path is, all my velocities are unitless, right? So this becomes a mean free path, and without that factor it becomes a mean free time, okay? Yeah, so for me, mean free path and mean free time are the same because they're not quite the same. They are the same if you have massless particles where the velocity is the speed of light. Yeah. And the third length scale is the so-called hydrodynamic length scale, L hydro. This is a macroscopic length scale, and it tells you the length over which the system varies macroscopically. So it's controlled by gradients of the temperature, gradients of the energy density, gradients of the baryon number density, or gradients of the velocity profile. So the inverse of that length scale is proportional to the expansion rate. So if u is the expansion velocity, this is the divergence of the expansion velocity. I write it as a 4 vector, and we call that quantity theta. This is the scalar expansion rate. And you can take that as representing the hydrodynamic, the macroscopic hydrodynamic length scale, with the argument that when you have a density in the when you have a gradient in the temperature or gradient in the energy density, you have a gradient in the pressure, and a gradient in the pressure gives rise to a hydrodynamic force, and that leads to expansion. And so in any case, whatever you do, any type of gradients, eventually they lead to an expansion. And this is a scalar expansion rate. You can also have velocity shear. They are all parametrically similar to each other. So, for example, the expansion rate is parametrically of the same order as any energy density gradient, normalized energy density gradient, and so on. Yeah. Question? Okay. So these are the 3 length scales. And now we will look at how they are related to each other. And depending on how they are related to each other, the system will have different characteristics. So the first, these 2 here are microscopic length scales. This here is a macroscopic length scale. Yeah? So let's first look at the ratio of the 2 microscopic length scales. Study ratio of the microscopic. So I'm looking at the ratio of the mean free path over the thermal wavelength. Okay, according to what I wrote here, this is proportional to 1 over sigma times n. Now I'm dropping the factor of v that Francesco didn't like to begin with, and the thermal wavelength. Let me regroup these factors. So this is 1 over sigma times lambda thermal times 1 over n. Now, if you have a system that is basically made up of massless degrees of freedom, in close to thermal equilibrium, there is one number that you need to remember, namely that in a thermalized system of massless degrees of freedom, every degree of freedom has 4 units of entropy. This is exact in the Boltzmann approximation. It's a little bit less. It's 3.6 units for Boltzmann particles, for Bose particles, and it's 4.2 for Fermi particles. So remember, just 4 units of entropy for a massless degree of freedom in thermal equilibrium. So I can replace this up to a factor of 4 by the entropy density. S is the entropy density, particle density, entropy density. And then if I use the fact that you can read in textbooks on transport theory that transport coefficients like the shear viscosity or the bulk viscosity zeta, this is eta, this is zeta, this is bulk viscosity, or the heat conduction, actually temperature times the heat conductivity. So kappa is the heat conductivity. These are quantities that don't exist in an ideal fluid. They describe slight deviations of the system from local equilibrium. And you can show from kinetic theory, and I'm anticipating that here for the purpose of making my argument, that this is proportional, inversely proportional to the average cross section and the thermal wavelength. And if you have massless degrees of freedom, then you can write this as lambda mean free path times t to the 4th, because just by dimensional analysis and the fact that temperature is the only scale in the system, this is an area, so it has to go like 1 over the temperature squared. This is a length, so it has to go like 1 over the temperature. The mean free path also goes like the temperature, so I can write this as lambda mean free path times the 4th power of the temperature, which is how it comes out from kinetic theory. So if you know that from your textbook on kinetic theory, then you see that this factor here is something like so this is something like eta over s, or zeta over s, or kappa times t over s. And so all of these are parametrically of the same order, and they are given by this. So in other words, this ratio here, lambda mean free path over lambda thermal, gives you is a measure for the viscosity in units of the entropy density, shear viscosity or bulk viscosity, or the heat conductivity in units of the entropy density. And when you check it out dimensionally, you have to sit down a little bit. You will find that these ratios are unitless, as they should be, because they are the ratio of two length scales. So eta over S is called the specific shear viscosity, or the shear viscosity per entropy density ratio. This is the specific bulk viscosity, and this is the specific heat conductivity. So this ratio of these two length scales tells you about these transport parameters, and we can accordingly subdivide the type of media into 3 classes of possibilities. The first is the so-called dilute gas regime. The dilute gas regime is when this ratio, lambda mean free path over lambda thermal, is large. So let me take eta over S as representing that ratio. If this is much larger than 1, which means, according to this expression here, that the cross sections on average, have to be much less than the thermal wavelength squared, or much less than 1 over the temperature squared. So this tells you that the system has to be, in a sense, weakly coupled. So you have to have small cross-sections on a natural scale, which is given by the inverse temperature squared. And then we have the weakly coupled or dilute gas regime. So it's characterized by eta over S values, which are large compared to 1. So this is the weakly coupled, weak coupling regime. Now, the second regime is when this ratio decreases to something of the order of unity. So instead of being very much larger than unity, you get somewhere too close to unity. So this is the so-called dense gas regime. This is lambda MFP over lambda thermal, which is, or eta over S, of the order of 1, which means that the cross-sections are of the order of 1 over the temperature squared, no big factor between them. In this case, we have what is called a dense gas. The difference between a dilute gas and a dense gas is the following. When you have a dilute gas, you have a large mean free path to the relative to the thermal length scale. And large mean free path means that between collisions, you have well-defined energies of the particles because of the uncertainty relation. You have enough time to actually give the particles a well-defined energy. So you can actually describe them as particles that are on their mass shell, and this kind of description makes sense. So in this regime, you can describe the system as a system of quasi-particles which have a well-defined relationship between their energy and their momentum, and which is constrained by the mass shell. This is where the Boltzmann equation is valid. The Boltzmann equation applies for particles that are close to their mass shell. When you have a dense gas where the mean free path becomes comparable to the thermal wavelengths, then the energy-time uncertainty relation tells you that you can no longer give the particles a well-defined relationship between energy and momentum. If you would write down the quantum field theoretic propagators for these particles, they would be described by a spectral density, which is no longer a delta function. So here, in this regime here, we have a spectral density, rho of P and E, which is delta of P squared minus M squared. If you are in this regime, because of the collisions, this spectral density here, rho of E and P, becomes something that looks like, let me look at my notes here, that looks like E squared gamma squared of temperature, and then you have E squared minus P vector squared minus M squared thermal squared plus E squared gamma squared over the temperature. So if you plot this, so here is, so you do this as a function of energy, as a function of energy, you plot rho for P fixed. Then this delta function would be a delta function peak here at E is equal EP is equal square root of M squared plus P squared. And when you go to the dense regime, the interactions between the particles are strong enough to do two things. First of all, they provide the particles with an effective mass in medium, something like a +1 mass, and that means they shift the mass of the particles by an amount that is proportional to the strength of the coupling. So we go from M squared to M squared of T, where at weak coupling you can write this as some coefficient times G squared T squared if the coupling is weak. So the first thing is that the particle acquire a dynamical mass that describes the strength of their interactions with each other, with a medium. And the other thing is that they get a collisional broadening, so their spectral function gets a width gamma, and it's no longer given by this delta function, but by a Lorentzian that is written here. So the function looks now like that, where this here is now square root of p squared plus m squared of t. So if I write it out, this m squared plus some number times g squared t squared. So that peak has been shifted, and then there is a width gamma here, and gamma of t is of order some other number times g squared times the temperature. So it has 1 unit of the temperature. Gamma squared would be t squared times not g squared, but times g to the 4th. So the width at weak coupling, the width, so if you write it like that, then you find that the width is smaller than the mass shift. It's of a weaker effect for weak coupling. When g is of order of 1, then both of these effects can be equally big. And here, then at sometimes twice the mass, twice the mass of the particles, you can just have pair production of particles, and those the spectral function becomes finite and eventually it just becomes flat at high temperature. That's not what I'm interested in. I'm interested in this quasi-particle picture. So in the dense gas regime, you cannot ignore that width anymore. And that means that if we want to describe things in terms of kinetic theory, we can no longer describe it in terms of the Boltzmann equation, which is based on quasi-particles on their mass shell. You have to replace the distribution function in the Boltzmann equation by something that's called a Wigner distribution. And the Wigner distribution exists also for energy values that are not equal to p squared plus m squared. And you have to write down a kinetic equation, a so-called quantum transport equation for the Wigner function. And this is something that has been explored theoretically to quite some extent, but there are very few numerical implementations at this point, just because it is more involved to propagate something that has 4 independent momentum variables than something that has only 3 independent momentum variables. But if you look, for example, at the Gießen code of at the Frankfurt-Gießen code, PHSD, parton-hadron string dynamics, it has a quark-gluon plasma phase, which is based on quasi-particles that have spectral functions that have this type of structure, and so they have a thermal mass shift embedded, and they have a thermal width embedded, and that's one approach that takes this Wigner function approach. And finally, the third regime, let me keep that here for a while. The third regime is that of a liquid. The liquid regime is what you reach when this ratio lambda MFP, the mean free path over the thermal wavelength, or the specific shear viscosity, becomes small compared to 1. This is where these mass shift effects and width effects become so big that that this spectral function has no longer a recognizable peak, and in that case, you can no longer even talk about the concept of a quasi-particle. The system has no quasi-particle substructure. Kinetic approach like Boltzmann equation or even a Wigner function approach is completely inapplicable. And if such a system reaches a state of local thermal equilibrium, it will not be a gas anymore, it will be a liquid. Yeah.
Completely agree with what you said. But I have a remark about the names that you gave to this regime. If you take a glass of water,
Mm-hmm.
lambda mean free path of the lambda thermal is much less than, is much larger than 1. And still it's a liquid, according to say the
Is that really true? Yeah, okay. Yeah. Because of the masses of the molecule. Yes, right. Yeah. Right, yeah. So this way of classifying systems is geared to massless particles. Yeah. So when you have a mass in the system, then you have actually more length scales in there, and you have to subdivide this further according to the ratio of temperature to mass. And so, yes, okay, it gets even more complicated. Let's not do that today. Yeah, right. Yeah. Well, for massless systems, that is the correct set of names. Yeah. Yeah, right. Well, what Francesco is saying, that you can have a liquid regime even if this is the case, if you have another mass scale in the system that drives you into the liquid regime. If you have no masses, then you cannot get that. You can get a liquid only for this set of parameters.
I think this is a special regime because you are comparing something which is quantum, so the lambda thermal, with something which the interaction scale, which is lambda with the bar.
Mm-hmm.
So for instance, in a glass of water, you have another scale, which is the density of particles. And so the system is the liquid because the mean-free part is of the order, the mean-free part is of the order of 1 of the square root of the density.
Mm-hmm.
This is why it's a liquid. So it means
Yeah.
that the molecules of water in the liquid phase, they collide every time they see each other.
Yes.
Well,
Mm-hmm.
but the thermal wavelength is extremely small, so the quantum scale, because they have a large mass. So it is
Yes.
one square root of
Yeah. Right. That's right. So yeah, that's right. So what I was using, and I think I wrote that here, is that the thermal wavelength goes like 1/t, which is true only for massless particles. For non-relativistic particles, the thermal wavelength goes like 1/square root of m times t, and then the whole counting goes differently. Yeah. So I'm not using that, I'm using that. Okay, so this is the strong coupling regime. So you get a liquid into the liquid regime if you have strong coupling. You are in the gaseous regime when you have weak coupling. When you have weak coupling, you can use the Boltzmann equation as an approach. When you have strong coupling, you cannot, but you can still describe it hydrodynamically, which is something else that I want to discuss now. Okay, so this was the three regimes that you get in this simplified situation for massless degrees of freedom when you just compare the two microscopic scales with each other. Now let's go to a second stage of characterization, namely looking at the microscopic scales relative to the macroscopic hydrodynamic scale. So it is convenient to introduce a ratio here, which is called the Knudsen number, Kn, which is the ratio of the mean free path over the hydrodynamic length scale. And I'm going to use the scalar expansion rate as a proxy for the inverse hydrodynamic length scale. So it's lambda mfp over L hydro. And since the inverse of L hydro is proportional, it's parametrically equal to the expansion rate. This is the product of the mean free path with the scalar expansion rate, with the divergence of the flow field. So if we plug in the definitions of the mean free path, we can write this as eta over S times the thermal wavelength times the expansion rate. And so using that for massless particles, the thermal length is proportional to 1 over the temperature. We can write this as eta over S times T times the expansion rate, and eta over S times T is proportional to the relaxation rate of the system. So this tells you how quickly the system relaxes, so that you can write this as theta times the relaxation time in the if you use the Boltzmann equation in its relaxation time approximation. So these are different ways of writing the Knudsen number. They are all proportional to each other with numbers of the order of magnitude of 1. And so I will try to characterize the Knudsen number by shear viscosity multiplied with expansion rate, or by relaxation time scale multiplied with expansion rate. So here the three regimes are that of ideal fluid dynamics, ideal fluid dynamics is the limit where the mean free path can be completely neglected compared to any macroscopic scale. So mean free path becomes extremely short when you look at it from a macroscopic point of view. You can ignore the fact that there is a finite mean free path. You set the Knudsen number to 0. That gives you ideal fluid dynamics. So Knudsen number approximately 0, so this is equivalent to either eta over S being small, close to 0, or the expansion rate being close to 0, such that the product theta times tau relaxation is approximately 0. So you can have ideal fluid dynamics even if eta over S is large, even if the system has gaseous behavior. So remember, large eta over S means large mean free path over thermal wavelength. That's the dilute gas regime. So you can have hydrodynamics valid even if the dilute gas regime is the expansion rate is sufficiently small. So that even though that factor is large, this product is still close to 0. This is why hydrodynamics works when I describe this kind of... I'm sorry. I was trying to get a little bit of air moving here. This is a perfectly hydrodynamic. You can describe hydrodynamics to describe that airflow that I can make by opening the door quickly here. Or you can be in a situation where the system expands extremely rapidly if the shear viscosity is correspondingly small. So if the mean free path is small, very, very small, then you can accommodate even very rapidly expanding systems and still describe them hydrodynamically. This is why hydrodynamics works in heavy ion collisions, because in heavy ion collisions you do have huge expansion rates, but you also have very small shear viscosity. This is something that we know. On the other hand, it has been learned in the last 10 years that there is a lower limit to this ratio eta over S, a fundamental lower limit that is imposed on you by the uncertainty relation. The viscosity is related to momentum transfer from one fluid cell to neighboring fluid cells. So there is a delta P involved. You cannot have that over infinitely short distances or times. And therefore, there is a product, there's an uncertainty product, which in the end leads to a lower limit of eta over S. If you want to describe that, you can try to describe it with the Boltzmann equation, but then you cannot really get to the lower limit because the Boltzmann equation only works when eta over S is large. This was tried by Danielewicz and Julashi in 1985, I think. They wrote a paper where they tried to estimate the lower limit of the shear viscosity using the Boltzmann equation, which is not really consistent to getting at a lower limit. They found a ratio of 1 over 15 as the lower limit. In 2001, and then later with more work in 2003, in 2003 and a little later with more work in 2005, Damson and his younger collaborators published papers where they used the fact that when you go to strong coupling in quantum field theory, you can actually map it to by the so-called Andy de Sitter conformal field theory duality, which was discovered by Maltasena in superstring theory. You can map a strongly coupled quantum field theory onto a weakly curved space-time in 5 dimensions, and you can map the calculations that you want to do in a strongly coupled field theory into manipulations of the Einstein equations of motion in that curved space-time. And they were able to, so they implemented a heat bath in the field theory by putting a black hole in that 5-dimensional space. That black hole has a event horizon which, according to Hawking, radiates Hawking radiation at a given temperature. That gives the temperature to the heat bath. And they did some mumbo jumbo in there that allowed you to calculate the shear viscosity in that heat bath in the limit of infinitely strong coupling. And they found, and that's a more reliable calculation, they found eta over S has to be larger or equal than 1 over 4 pi, which is 1 over 12. So the 1 over 15 that Girashi and Danielewicz got was actually not that far off. The only quibble is that it was obtained in an intrinsically inconsistent approach, whereas the Son calculation was done in a consistent fashion. I put here a larger or approximate because it has, originally they thought it was a firm lower limit. In the meantime, people have found specific cases where eta over S can actually be smaller than 1 over 4 pi. But always when they found values that were significantly smaller than 1 over 4 pi, they did it in theories where they had to, which became inconsistent. So it's firmly believed that 1 over 4 pi is a good marker for the domain of lowest shear viscosity, and you cannot get much below that. And so that means there is a lower limit for this, and that means there is an upper limit for the expansion rate that you can accommodate, and hydrodynamics still being valid. And this upper limit for the expansion rate gets violated in heavy ion collisions when you go to very early times, because of the boost invariant expansion that you start out initially. So initially, the expansion rate goes like 1 over the proper time, and when you go with the proper time back to 0 to the point of collision, this becomes infinitely large, and therefore this product can no longer stay near 0, even if eta over S is as small as it could possibly be. So ideal fluid dynamics does not work clearly at the very earliest stage of a heavy ion collision. It also does not work at the end of a heavy ion collision. There the reason is different. At the end of the heavy ion collision, this is no longer a problem. So the expansion rate actually settles down and becomes smaller, but at the end of the heavy ion collision, the mean free path between the particles gets very big, and when the mean free path gets very big, lambda MFP over lambda thermal gets big, and this ratio gets big. So at the end of the collision, hydrodynamics breaks down because this factor becomes big. At the beginning of the collision, it breaks down because that factor becomes big. At the end, it breaks down because this factor comes big. In between, we have actually this condition that it's small, and we can use hydrodynamics. Now, if the Knudsen number is not exactly 0, but still small, you can correct ideal fluid dynamics by something that's called viscous fluid dynamics. So viscous fluid dynamics is valid as long as the Knudsen number is small compared to unity. Doesn't have to be 0, but it has to be small compared to unity. And that means that eta over S or the expansion rate theta have to be such that their product, theta times tau relaxation, is not larger than unity. And so that's the most relevant. That's relevant for our applications, because the ideal fluid dynamic approximation is really too rough for quantitative description of heavy ion collisions. But these viscous corrections allow us to correct for this, for the deviations from local equilibrium. And then at the end of the collision or at the very beginning of the collision, you get into a domain where the Knudsen number gets large compared to 1. And that's where hydrodynamics breaks down. Hydro breaks down when the Knudsen number becomes larger than 1, which means that eta over s or theta become big, so that such the product becomes larger than 1. And that's what I said happens at the very earliest and the very latest stage of a heavy ion collision. So we said that hydrodynamics, ideal or viscous fluid dynamics, can work even if eta over s is large, as long as the expansion rate theta is sufficiently small. And this means that there is a regime, there is a physical regime where you can describe the system simultaneously microscopically by using the Boltzmann equation, because eta over s is large, and macroscopically by using the hydrodynamic approach, because this product here is small. And this is the regime that I will use to derive the hydrodynamic equations from the Boltzmann equation. So I will use fluids that have that property, so they are dilute gases, but they expand sufficiently slowly that you can describe them hydrodynamically in order to derive the form of the equations. Now, the form of the equations does not rely on this particular assumption. What relies on this particular assumption is the equation of state that you get for the resulting system and the value of the transport coefficients, the value for the shear viscosity, the value for the bulk viscosity. They do depend on in which of these regimes they are, but the form of the equations does not. And the reason is that hydrodynamics is basically an effective theory, low energy theory that applies to these systems in the long distance limit. And so once I have derived these equations, then I can use them. I can use the same form of the equations in the regime where the Boltzmann equation is no longer valid. So I can go back to the strong coupling regime. What will happen when I do that is that the value of the shear viscosity will change. It will become smaller. The value of the bulk viscosity will change. It will become smaller. The equation of state will change. It will go from an ideal gas to something that is an interacting gas. But the equations will not change. And so once we have established the equations, we can use them in the strong coupling regime where there is no Boltzmann description microscopically anymore, but we still have a hydrodynamic description. We have to take a break, right? Yeah.